continuing on with learning target 5.8, the law of sines. We've got this example question where it says two stations are on an east-west line 110 miles apart. And so that's what's included on this drawing here. Here's station A, here's station B, and they're on the east-west line, and they're exactly 110 miles apart. Then it says a forest fire is located on a bearing of north 42 degrees east. So here's this forest fire, and so from station A, it's on a bearing of going from north 42 degrees to the east, and so that's what's labeled there. And a bearing of north 15 degrees east from station B. So again, going off of what's called true north, only 15 degrees to the east. And the question is, how far is the fire from each station? So we want to know how far is the fire from this station and how far is the fire from this station. I think it's sometimes helpful to draw, have a drawing with the labeling and everything like that on it, but then also just get one simple triangle where you don't have all the extra lines in there. You just have the information that you need. So for example, we need to know this angle. And I know that this one is 42 degrees. And because the north and east lines meet at a right angle, we can subtract 42 from 90 and get a 48 degree angle here. Okay. We're also going to need to know this angle at B. And so because this north meets the east-west line at 90 degrees, and then it's an extra 15, we can label that as 105 degrees. Okay, and then of course we've got the 110 miles in between. So we've got two angles and a side. That tells us that we can use the law of sines. But in order to use the law of sines, you have to know an angle and the side opposite. So for example, if we know this 48 degrees, we would have to also know this side opposite. We don't. Or since we know this 105 degrees, we would have to know the side opposite, and we don't. That's what we're looking for. And because we know this 110, we'd have to know the angle opposite, and we don't know that one either. But because we have two of the angles already, we can pretty easily solve for the third by adding up the two that we know and subtracting from 180 and get 27 degrees. Okay, so now we can use the law of sines. I will label this side as lowercase b and this side is lowercase a, and now we can just set up those equations and say, let's solve for a first. So now we can say that a over the sine of capital A, which is 48 degrees, has to equal, and now we have to use the side that we know. So because we know this lowercase c and capital angle C, we can do side C is 110 miles over the sine of angle C, which we decided was 27 degrees. So now when we cross multiply and divide, we get A is 110 times the sine of 48, all divided by the sine of 27. So A is approximately 180 miles. I think it's like 180.06, but we can just round it and say it's about 180 miles. And then to solve for side length B, we have to use side B and angle B. So I will say that B over the sine of angle B has to equal, and again, we can use either one now because we know both for C and both A's. But because that one is a little bit more accurate, I will use the 110 miles over the sine of my 27 degrees. And we can do the same thing, cross multiply and divide. And so B would be 110 times the sine of 105, all over the sine of 27. And we can round that when we type it in and get approximately 234. It's like 0.04, but we'll just round it and say it's about 234 miles. Okay, if you're not getting those answers, check your calculator. It might be set to radians instead of degrees. Okay. With the law of sines, it is possible to have what's called an ambiguous case. And so an ambiguous case is only going to occur if you have two sides and a non-included angle. and there might be more than one option possible. Okay. So here's this table that you don't have to fill in anything, you just have to kind of understand what it's saying. So for all these cases, you're given the measure of angle A and then the side A, so that means you know the angle on the side opposite, and then another side, side B, and it could be side A just as long as you know this angle and the side opposite. So one option might be that if you're given this angle, we don't know how long it is, but it has to be exactly this angle, but then we do know how long this side is. Well, what if this side A happens to be really, really short? It's not going to be able to touch down to this side, and so that means that there's actually no triangles possible. That would be a triangle that doesn't exist. There's two options then where you're stuck at there's only one triangle possible. Okay, and one of those is where, again, you've got this side can be of any length. You don't know how long that is, but you do know exactly how long that side is, and you know exactly how long that angle is. And so if A happens to be the height where you drop it down only, to make a perpendicular, then there's only one place that can end up. It can't end up anywhere to the left. It can't end up somewhere to the right. It has to be straight down, and there's only one triangle possible. Okay, and that's where the sine of B equals 1, right? Because the sine of a 90-degree angle, you know, is 1. And where A equals H, which is less than B. So again, that height of the triangle is the same as A. There's only one triangle possible. Okay. Another time where there's only one triangle possible would be this situation here, where A is much, much longer. And that's because there's only one spot over here, because if you looked and saw where would it end up over here, well, then our angle would be different. Okay. But here's why we have to call it the ambiguous case, where it's not necessarily certain. If you know this one has to just be, set at that length, and this one is going off at this angle and it's stuck right there, and I tell you that A is the shorter piece, but it's still longer than the hypotenuse, there's two different places that you could have it. It could be over here or over here. I kind of think of this one as like a kickstand almost, so it can be either bumped out or it could be bumped in, but there's these two possible triangles. There's this one over here to the left, and then there's this much bigger one, but they all still have the same requirements. Both of those little triangles have this angle, and this side length, and this side length. It's the same as having this angle, this side length, and that side length. You can just end up with two different triangles, and that's why it's called ambiguous. You can't be certain which one you're talking about. Here's another way to look at it. This one's on page 278 of your textbook, and so if you want to have another way to kind of visualize it, you can look at that page on your textbook, and it goes through that explanation as well. It's the same information as the previous page, it's just given to you in a little bit different format. Okay. And so here's a problem that it says, solve the triangle. They're both already solved. So this is that ambiguous case that we were talking about, where we know that this is 55.3 degrees. And we know that this side is exactly 24.9. It's the exact same as that being 55.3 and this side being 24.9. And then it tells us that side A is 22.8. So it could be 22.8 and meet this line over here, or it could be 22.8 and meet this line much closer. So we end up with two very different triangles. Notice, though, that there is something that, well, you might not notice it, but I want to point something out about this angle here of being 63.9 degrees and this angle of 116.1. Those two angles happen to add up to exactly 180 degrees. So what's the relationship? Why does those two work? So what's the relationship between our two different possibilities? add to 180 degrees. Okay. The reason for that is because when we set up our law of sines equation, we would use 22.8, this opposite side, over the sine of 55.3. Whoops. Has to equal this opposite side, 24.9, over the sine of 63.9.